how to design your reinforced concrete beam due to shear, and we can figure out what is the spacing between your stirrups. Just a reminder, stirrups are the main steel reinforcement used to support shear force and torsion. Actually, for shear, we have two contributions. One part from concrete, the second part from steel. For concrete equal to B web times B times square root of C FC prime. From steel reinforcement, we have contribution from stirrups equal AV FELD divide S. AV is the area of the legs of your stirrups. To design from the beginning, to design for your stirrups, we need to figure out what is the shear force diagram, what is the contribution from concrete, what is the area for legs of assumed stirrup. Then we have three situations. The first one, if this condition valid, we don't need stirrups, we will use the minimum. If this option or this situation is valid, then your spacing between stirrups will be this one or this one, the smallest value. If you have large amount of shear force, then you need to figure out what is the value of BS, and then you can figure out what is the spacing. Once you get spacing between stirrups, you need to check. This spacing must be smaller than the maximum spacing. Maximum spacing, we have to also two situations. The first one, smallest between the depth, divide 2 or 24 inch. The second one, based on what is the value of BS. So we have this situation or this situation. And we did two examples last time. The first one, we don't need stirrups. The second one, we need stirrups, I think I remember, was 5-inch spacing. We started also to understand what is the meaning of torsion. Torsion is twisting of your structure. Twisting, not structure, twisting of your member. So your beam, we have slab supported with your beam. This slab would like to rotate, to twist your beam. So this beam right now under the effect of torsion. This cantilever with this concentrated load would like to twist your beam. So right now this beam under the effect of torsion. Curved beam under the effect of torsion. This beam in space with this concentrated load, this part would like to rotate the longer one. Do you know when we can expect torsion in your column? We will do some calculation right now, but we need to understand something first. Do you know when can we expect torsion for your column? It's horrible. It's very critical to your structure to find this torsion in your column. Do you think when? We don't like it.
It happens when you have
It's gonna be
quakes and stuff.
earthquake?
Earthquakes.
Perfect. When? All earthquake will cause torsion?
Sir.
All earthquake. Your earthquake will come to vibrate your building, the whole building, in one direction. So where is your torsion?
Lateral.
Okay. For earthquake, but in a specific situation.
With the wind.
Here is your isometric of your building. And here is your floor of your building. Okay? That's fine? And we can expect something called earthquake. So we didn't cover earthquake in our course or previous courses. So anyway, earthquake looks like wind load. Looks like concentrated load at each floor. Okay? But this load at this point called center of mass. Remember, your floor, one floor has walls, beams, slabs, live load, dead load, all of this stuff on your floor. That's right. Where is the center of mass? Where is the centroid for all of these loads? Maybe at the center of this area, maybe not. Anyway, but at the center of all of these weights, here is the application or the center or the point of application of your earthquake force at each floor. That's fine? Who is supporting or resisting your earthquake? Column? Yes. Sometimes your column looks like this. Sometimes your column looks like this. Around your elevator. Sometimes your column, something looks like this. In high-rise building. Made from concrete. I'm not talking about steel. It's not channel steel. No, it's concrete. Column. But this shape. This also column, but with I shape. It's not steel. It's concrete. So all of this stuff will be in your building to resist lateral load, earthquake. Actually, we have another point. I'm not sure where, called center of rigidity. This column has inertia. This column or this shape of column has another inertia. This shape of column has another different inertia. We have many in your building. Where is the centroid of all of these inertia? Centroid of these inertia for this vertical member, which is called column, called center of rigidity. Your building will rotate around center of rigidity. Your force acting at point of center of mass. We have eccentricity in between. If you multiply this force by this eccentricity, you can expect torsion of your building. Then your column will be under the effect of torsion, under the effect of torsion, under the effect of torsion. We hate this situation because torsion is a brittle failure. Suddenly, you will find your building collapse. You got it? What is the solution? We need to avoid this torsion. Okay, we cannot avoid these forces. It's the forces coming from your earthquake. So what should I do? Torsion equal force time distance. I cannot cancel my force. So what should I do? Cancel your distance. Make this point coincide with this point. Make this the distribution of your column uniform distribution in your building. Fatal mistake. If you have floor plan and you can find very strong column at this location only and very weak column on the other, that means the center of rigidity will be on this side. Most of the time, center of mass at the middle. So we have eccentricity, and force time eccentricity can make torsion. So if you decide to put very strong column in one side of your building, please put another strong column on the other side. If you decide to put very strong column in this side, go ahead and put the same on the other side. Not the same, but make equivalent. To maintain your center of rigidity to coincide at the middle with the center of mass. If you can, delete, that's perfect, but we cannot. If you can reduce this eccentricity, so force time eccentricity equal torsion. If you can reduce, because I cannot reduce earthquake forces. It's coming from earth. So I can reduce the eccentricity. If you can reduce this force, this eccentricity, you can reduce your torsion effect. You got it? Go ahead.
If you put a strong, what do you consider a strong column in the middle of the building? Would that?
Yeah, sometimes, yeah, that's fine. But location of your column, it's not depend on my decision only, but what is the architecture plan of your building.
I don't care about the architect at this point. I just
No, you
talk
have to
about the
respect it.
structural.
Yes. Yeah, but the first thing you need to respect it, the architecture. I cannot, I have a hall or stairs or whatever, I cannot put column at the middle, you know?
Yeah.
So I have some limitations for your distribution, but as a structural engineer, be careful. If you try to put some column, strong column mean big column. In one side, maybe at the edge, you have to put another one or maybe two equivalent to the strongest one to make your center of rigidity in between. This one is more advanced for which called high-rise building design and analysis. Okay, any question? Because torsion is nothing, just few equations, we will cover it, and one example, and that's all. But what is the idea behind this one? It's a very critical point.
So we don't want it to twist, but if it does just come straight at the column, then the rebar or what's helping?
Yeah, we will design right now how can I put stirrups to resist this torsion. Okay?
One more question.
Yeah.
So, like, being in California, maybe you account for that more, and then here in Texas or
Yeah,
in
yeah.
places?
Yes, it depends on do you have seismic activities or not
Yeah.
in your area. So we have two parameters right now. Your torsion will be force and eccentricity.
Yeah.
What you are talking about, what is the value of your force based on your location? Then what is the eccentricity based on your distribution